Okay, so is MIP mapping the best we can do? We saw that it introduces some blurring. So now there's a question of can we do better? So MIP mapping happens isotropically. This means that it's the same in every direction. So anisotropic means not the same in every direction. So let's take a look at this. So here's our screen space. And so for each pixel in the screen space, we can ask how does it map into texture space? So some map to tiny little areas and some map to larger areas in texture space, but they don't map to squares that are nice axis aligned things like what we have stored in our MIP map. So maybe we could do better if we could somehow add up what's going on inside of this area rather than adding up a big square. So let's look at this example. So here's a straight road going out. So this is with trilinear MIP-map filtering, and this is with anisotropic filtering. We wish we could get this. You see how it doesn't get as blurry in the background. So what's going on? As we stretch out, our one pixel here is getting stretched out in the V direction, but not so much in the U direction, right? Our close pixel just maps to one pixel here. But this thing in the back stretches out to be taller than it is wide. And so if we could somehow get rectangles instead of squares, we could reduce the blurring and get some result like this. So it turns out in 1984, the next year after the MIP mapping paper, somebody came along and said, hey, I can do better than MIP mapping. I have an idea. So this used summed area tables. And it's hard to see in this, and I'll show some additional examples, but this is supposed to be the nearest neighbor, and then this is MIP mapping, and this is summed area tables. And the idea is to show that it does better. But first, let's take a look at what are summed area tables. So summed area tables say in each pixel, we're going to store the sum of all pixels up to that point rather than the pixel itself. So if we consider this whole region in the yellow box from the corner all the way to here, if we summed all these pixels up, they would sum to 450. And if we summed all the pixels in this red section, those would sum to 101. Similarly, if we summed everything in this section, it would sum to 186. So now how can we calculate an arbitrary rectangle that's not going to necessarily have to be square? So if we wanted to calculate this rectangle, the red one, A, B, C, D, we could take this whole sum, but now it's too much. So then we could say, well, we didn't want this side part, subtract this. We didn't want this top part, subtract this. Oh, I accidentally subtracted this corner twice, so add it back in. So that's what we see here. If we want to calculate this area, the sum of the things within that region here, right? The purple here. What's going to be inside this purple is 15 plus 16 plus 14, 28, 27, 11, right? So that's some sum of things. We're going to take this plus this minus this minus this, which is what's written here, and it's going to come out to be the same thing. So now we can just do 4 texture accesses rather than some potentially large number, right? So why didn't we just sum them up by hand? Because there might be 10,000 pixels in here, and we don't want to have to go do that in real time. So this gives a way to do the math quickly to sum this up. So what do we get? So here's nearest neighbor. We haven't done anything. We just look up. This gets us noisy stuff in the back. Here's MIP mapping. So we get a little bit blurring in the back where it didn't have to be, right? So we want to get blurry back here, but over here we got over blurred, and summed area tables can clean some of this up. So this can produce a nicer result. Now this isn't what's built into OpenGL, right? MIP mapping is a built-in primitive. You would have to do extra work yourself to try to deal with summed area tables, but it's a way to get an even higher quality. So can we do even better than this? So MIP maps gave us a square region that we're trying to sum over. To approximate, our pixel was in some shape. Summed area table said we'll get a rectangle to approximate this. Somebody else came along and said, well, I could use an ellipse. This is called elliptical weighted averaging, is what the EWA is elliptical weighted averaging. So we can put an ellipse that fits this. And in addition, instead of weighting every pixel equally, we're going to use some kind of weighted cross blend, right? So like this is the weighting on each pixel that we're going to add up, rather than just using an equal weight on all of the pixels. Okay, so we have a more complicated shape that better approximates the things that we wanted. So suppose we do this. What do we get? So here's elliptical weighted averaging with a sample texture map, and it's pretty good going all the way to the back. So as a comparison, here's what we wish we got. This is as close to ground truth as we're going to get to graphics. Let me go back. Here's elliptical weighted averaging. It's pretty good. So we can do filtering like this and potentially do even better. Just as a reminder, here was MIP mapping, right? So we have significant blurring in the path with the MIP mapping. So improving our filters can have an effect on how our texture maps into screen space. Now, are you going to have to deal with any of this? No, you're going to put textures on your objects in your assignments. We're not going to deal with any of these things in the assignments in this class. But it's useful to know that when you're seeing these kinds of effects, there are ways to go and deal with it. So here's just another example. This is point sampling. So we can see we have noise and weird stuff happening in the back. If we could try linear interpolation on a pyramid, this is the MIP mapping. So we can see it blurs out the back, but it's still got weird stuff. Summed area tables, still got some problems. And then when we go to elliptical weighted averaging, we can get much nicer results. So stepping up what we're doing can improve the results of what we're getting.